Hello, welcome to another problem session. So today we have a very familiar problem that is a kind of like a fake system. You have to actually only interpret it mathematically. So what it is, you have a infinitely long wire. Infinitely long wire doesn't exist in physical nature, right? So it's just a mathematical thing. Now its current is going through some steady current of a steady current, should have been steady current. See how difficult it is to specify the problem so that you can get the answer properly. So steady current, and I have a point P which is a distance S from there, and I want to know what's the magnetic field over here. What's the BP? Magnetic field is a vector, so I want to know the direction and the magnitude. You already know the answer to this problem. Probably memorized it somehow, and maybe you did this using Ampere's law, but we're going to do using Biot-Savart law. Okay. Now Ampere's law requires some additional arguments that you have to use, like a symmetry argument, but we're going to do Ampere's law properly in a future video. But right now we are doing Biot-Savart law. So okay, so Biot-Savart law says that this law says that the magnetic field at any point P is equal to mu naught, and for this is for the steady current. Current is steady, so it comes out of the integral and go over the circuit. What are the current is the circuit or branch, whatever. Got to integrate over a extended structure. This integral dl is an element of the circuit. So if the circuit is going this way, if the current is going this way, the dl over here is this way. Over here dl will be that way. So see the dl direction changes. Over here dl will be that way. So but in our case dl will be all along this, right? Cross, once you pick the element and the point is P is here, we need to know from this element to that vector. And so there's a direction vector u hat, magnitude 1, dl to point P, and then divide by this distance, whatever distance is r square, dl to P. I like to memorize this way. This is just a formal definition, right? And I need to able to get this answer to this problem by somehow casting this problem so that I can do this integral. If somebody told you can do physics without math, probably not true, because you can do some part of physics without math, but it really requires calculus, all right, to do a lot of physics. Here, of course, it's really require calculus 3, or like the later multivariate calculus, all right. Anyway, I hope you had those calculus courses and you have kind of, this is not the place you're learning how to do integral. Here you're learning how to set up the integral for a problem. Okay, so this is going all the way to infinity this side, and minus infinity this side if it's an axis. So if this was the z-axis, then this will be plus infinity, this will be minus infinity, z equals to minus infinity, z equals to plus infinity. This we can't do that, right? This is setting the integral, and this must be a part of physical system. So here is a physical system that the wire is, so it's somehow connected to something, and the current is steady current I going through this, and this part is straight, and we have we can point P, we can just orient the axis so the x-axis is in that direction the point P belongs. Okay, so this is in this, the whole thing is a SC plane, and the y-axis will be like this. Right hand coordinate system, the y-axis is that way, not drawn. coming out and then going in. Okay, so at this point, when you do this for this system, we can set it up. The interval will be well defined, and we get an answer. So this will be some kind of B when you have a length L wire at point P. Okay, so this will be a will depend on S, and not gonna depend on anything else. Depends on S, and then I'm gonna take a limit. L go to infinity, S finite. So I'm gonna keep the S fixed, but L go to infinity, and that's the way we're gonna do this in integral. Okay, so let's do it out. I'm gonna clean this up and then let's do it out. Okay, so we're just concentrating on this part, so I redraw it over here. So we at some point point Z, so this is Z. I usually call it Z prime because I'm looking at on the source, and the point P I use the regular unprimed coordinates, and so this is going to be Z prime plus DZ, and DL will be that. So we'll have a DL will be very simply dz prime k hat, and from here to here this is the r vector. We'll look at the point P. R vector is going to be just s I hat, and this where the dl is located, this I'm calling r prime vector. R prime vector will be just z prime k hat, and I want the direct vector. That's the direction we want. That's the u hat, and this is the r. So r in this triad of vectors, you look at this is r prime, and this is r, and this is, so to get to that place I can go this way or this way. So this way must be equal to this plus this, so r must be equal to r minus r prime, and as you can see s I hat minus z prime k hat, and u hat vector will be just divide this by its magnitude, so s I hat minus z prime k hat divided by s square plus z prime square root. Okay, so B at P, when the length is LOL, and so all the dependencies I'm writing there, that should be mu naught over 4 pi, steady current going through it, integrate minus L over 2, because this is the integration variable, to L over 2, and it's going to be S k hat cross I hat, it's going to be j hat, so j hat going to come out, and there's another video where I go and do this calculation, so if you want to go more detail, maybe go in that video also. Over here you can work this out yourself also. So S, so I'm doing DL cross U hat in my head. So U hat is this. So you have this is just K hat, and this is DZ prime in the numerator, and the denominator is R square will be this one more factor of this. So you get a S square plus Z prime square 3/2. Okay, so in interest of time, I'm just gonna write down the answer. Okay, so that's the answer of when L is finite. So I'm going to take a limit. You'll see a whole bunch of limit you can take. You can ask, so I'm going to do a limit B of P. This should be a vector. I have a depends on L. and s. It depends on other things also. It depends on I also, but I'm just going to do this. And s finite. So I'm looking at a finite distance from the wire, and I'm taking L go to infinite. So this kind of says if I have a wire and say this is length L wire and this distance is S, so this says S is much less than L. So this is the same thing as that. In physics, we can take a limit. There are the more rigorous way of doing this. You can expand this in a Taylor series and things like that. You can say S over L, let S be some quantity epsilon, and epsilon much less than 1. So how do you do that? If you have a function of epsilon and you're interested in epsilon much less than 1, so you expand it f0 epsilon equal to 0, df d epsilon equal to 0, epsilon plus d square f d epsilon square epsilon equal to 0, epsilon square over 2, like this kind of expansion. And this is what you would do physically to understand what's going on in terms of something infinite with respect to what. This is a very ambiguous limit. A lot of people do this, and I'm going to do this also, but the correct limit should be s over L going to 0. So you could think of this as like a not very good way of doing things. You can say instead do S over L much less than 1, or you can S over L going to 0 limit. Now that makes sense because this will be unitless. Over here L goes to infinity. What do I mean? L equals 10 to the power 50 infinity. Well, but that's going to be some kind of unit of distance, right? So I can take a small enough unit and can make as big as factor as I like. So this is not a very good way of doing this. Anyway, let's this is how a lot of people do it, and let's do that, and then we can also do that way. All right. So when I take this becomes infinite. This becomes infinite. So if this becomes large, this will come out of the integral and cancel. So this would be just means j hat mu naught I over 2 pi s limit of this thing. So this limit I'm going to, and this whole thing, it becomes 1, and this is the answer. Okay, so the answer will be BP will be if this was x direction, then is in that direction the y direction. This is z direction. So that's how we found by doing like that. So BP is one direct. But why would P be here? P can be at any distance s in any direction. P can be anywhere, so that I can say what does that mean? That just means I should use a polar coordinate. In polar coordinate, this will be the direction in which the angle moves, right? So this is, if I do like this is the y-axis and this is the x-axis. So this direction is the unit vector of the this is the direction of the unit vector of the angle. So what we got? Unit vector of the angle mu naught I over 2 pi s. So that's the complete answer for this problem. Now let's do it out more honest way, more this way. Okay, limit, take the limits in that way. Okay, so we want to take the limit here L goes to infinity limit, S finite. This we want to say let epsilon equals to, and now because it's factor 2 here, I can say 2s over L. It doesn't, and then we're gonna do B is just gonna be written as S is finite, some fixed number, so the B will be j hat mu naught I over 2 pi s, and this thing will be 1 over epsilon square root of 1 plus 1 over epsilon square, and then let's pull the epsilon out, 1 over epsilon out, and so this is going to be j hat mu naught I over 2 pi s, and it's going to be 1 over square root of 1 plus epsilon square. It's like that, right? The epsilon will cancel with that. So this is my function of epsilon, okay? And when I take a limit of this b depends on epsilon, limit of b depends on epsilon, I want epsilon go to 0, that will be j hat mu naught I over 2 pi s, limit epsilon goes to 0 of this f of epsilon, and this clearly is equal to 1, you know, so this is equal to 1. So j hat mu naught I over 2 pi s times 1. And so this is a much better way of doing it than taking the other way around. Sometimes we want a correction to this, okay? Say L is finite but not infinite. Say L is finite but large. That means we shouldn't just take a limit, we should say how it depends on L. And then in that case, we would do this way. We would expand in terms of epsilon. Do that out. Let's do that out. And then say, so we have f epsilon, which is 1 plus epsilon square minus half. We want to expand f0 is 1. Then f prime epsilon is minus half 1 plus epsilon square minus 3 half times 2 epsilon. And so that f prime 0 is actually 0, right? Because this is 0 and this is 1. How about f double prime epsilon? So 1 half, 3 half, 1 plus epsilon square minus 5 half times 4 epsilon square minus half 1 plus epsilon square minus 3 half times 2. Now this will means f double prime 0 is equal to 0, not 0. Yes, this part is 0 and this part is going to be minus 1. Okay, so we can say we found a non-zero thing, so 1 minus 1 epsilon square epsilon square over 2, yeah, epsilon square over 2. So I'm just expanding in terms of epsilon, not epsilon. I should have expanded in terms of epsilon square, which is, it's okay. I kind of didn't notice it can only be expanded like that. So this is the first term, non-zero term. Okay, so if I get this, then if I not use this but use this, we're gonna get a little bit approximation, which is not setting epsilon to 0. So B for a finite length at some distance, this almost equal to is in the j hat mu naught I over 2 pi s 1 minus, remember epsilon was 2s over L, so writing that out, 1 minus half times 4s square over L square. So this is minus 2s square over L square. So this thing captures finiteness of the length of the wire, but it is still large compared to the distance from the wire we are looking at. We're looking at here, if this distance is if the point is very near the wire, even if this is finite length, we'll have some correction here which will depend on the length. And sometimes you get asked this question, so you would not be able to get this answer if you go through the Ampere's law way of doing things, where symmetry requires you to kind of have already thrown away these parts. So these parts are only accessible through Biot-Savart law. So you need to know how to do this straight so-called infinite wire, when is not really infinite but simply too large compared to distance s. So when you have that situation, then you have no recourse, but you got to do it through the Biot-Savart law and expand using your Maclaurin series or Taylor series. Okay. All right. I know this is a lot of mathy things, but magnetism turns out to be it's quite hard compared to other parts of physics. You really have to first think in a three-dimensional situation. Somehow you have to have a formal part of the law, and then you have to convert that law into some workable, a math expression, which then you have to actually play around with. And the only way you're going to learn this by doing a whole bunch of problems. And you can actually go out to my website and try more problems there. So a lot of those problems are solved there. And if you haven't subscribed to this channel, you can go ahead and subscribe to this channel. It helps in get more people to access these websites, and it gets more distributed widely. And if you really like this kind of explanation, then maybe you can hit a like button. Okay, thank you for that. If you think there's something different you would like me to do, or some problems that you would like me to work on in this channel, leave a note, leave a comment, and I will try to get to them. Well, thank you and take care. Bye bye.